So by now in optimization, as a key concept, what you would have learned is that there is always certain condition given in the problem. And what you have to do is you have to, let's say, maximize or minimize the given quantity. Now, just before I start with the key concept, just a quick check on the uh, procedure to find maximum or minimum. So for any function, let's say y equals to f of x, you first find f dash x equate to 0, f dash x equate to 0, solve for x. To check whether there is a maximum or minimum at this x value, either you draw the sign diagram for single derivative, and if it changes from positive to negative, it is a maximum. If it changes from negative to positive, it's a minimum. So it's like decreasing and then increasing. This is increasing and then decreasing. And you can check by a double derivative test as well, that if your double derivative, you notice if double derivative is let's say less than 0, plug in this x coordinate that you got in double derivative. If it is less than 0, it is a maxima. If double derivative is more than 0, it's a minimum. So this is just your prerequisite. Now, typically an optimization problems look like where you have certain constraint. Like let's say I'm giving you an example here. Is that there is a cylinder that needs to have the volume of, let's say, 1 liter. The cylinder needs to have volume of 1 liter, or let's say for that matter 2 liter. What should be the dimension of the cylinder such that surface area or the material that is required to build this is, let's say, least or maximum? So whatever, I think you'll have to justify with the evidence that whether it's a maximum or whether it is minimum. So here the constraint that you see is that the volume should be 2 liter. Similarly, you would have seen in the prerequisite that, for example, if I'm creating a rectangular field, and the perimeter of this rectangular field can't be more than 200. So let's say this is 200 meters is the field. It should be, the perimeter should be exactly 200. You can design in whatever way such that area is maximum or minimum. So always there is going to be a constraint in the problem. So here, let us begin. The first problem is where you can see that there is a constraint of 2 liter as the volume of that particular solid. Now, volume of the cylinder needs to be 2 liters. So let's define the variable first. So the steps are, you define the variables. Let's say radius is r and height is h. So first step is, if variables are not defined, define them. So if variables are not defined, define them. So here the radius is r and height is h. And when you look at simply the use of these variable is going to be important. Now, volume of cylinder, we all know, is pi r square h. Volume of cylinder is pi r square h, and that should be equals to 2 liters. But since liter is not the correct unit to be used here, because radius and height will be in centimeter or meter, so we'll convert the this 2 liter as, let's say, 2000 centimeter cube. So 1 liter is 1000 centimeter cube. So we're going to use that concept. So 2 liter will be 2000 centimeter cube. Now, so height is going to be 2000 divided by pi r square. Now, why I'm doing so is because when you optimize, your problem needs to be only in one variable. Now, I have to, let's say, maximize or minimize surface area. So your problem has to be purely in one variable. So surface area will be, let's say, 2 pi RH. Assume this is a closed cylinder, 2 pi RH plus 2 pi r square. So 2 pi RH plus 2 pi r square. 2 pi RH plus 2 pi r square is going to be 2 pi r. Height is nothing but 2000 over pi r square plus 2 pi r square. So now you can see that I got surface area of this cylinder in either radius or in terms of height. So generally it is easier to get in terms of height, because then if you write down radius in terms of height, it becomes square root function. So by doing so, we got the surface area function in one variable. So radius and radius cancel, this pi and pi cancel. So you get 4000 over r plus 2 pi r squared. So now this is the surface area formula that decides the um, how much material is required with respect to the radius that you want. So our next step is to obviously do the derivative. Now derivative, since whatever quantity that is varying, with respect to that we're going to do. So derivative of surface area, so ds by dr with respect to r we're going to do. So before we do the derivative, just modify this a little bit. This will be 4000 r to the power -1 plus 2 pi r squared. So here the derivative will be 4000 -1 times r to the power -2 plus 4 pi r, plus 4 pi r. Now this is going to be negative 4000 over r squared plus 4 pi r. Now this needs to be equated to 0, because r to the power -2 can be written as r squared, hence it is this step. Now it will become 4000 over r square equals to 4 pi r. So 4 pi, I mean, this will be 4 get cancels like 1000 r cube. So 1000 equals to pi r cube. So this gives us r cube is 1000 upon pi, and if you do r will be cube root of 1000 upon pi. So you can find this value using calculator. So now once you got the radius of 6.83 on calculator, we need to check whether actually is the surface area minimum for this point. So already derivative is 0 at that point. That's step number 1 is crossed. Now what I'll do is I will find out the second derivative, and I'll check if my surface area is coming as maximum or minimum. So now this is like your verification step. I'll just erase this part. So just to check whether the surface area is minimum or maximum. So in verification part, you're going to do the derivative of this part. So derivative of 400 or negative 400 over r square plus 4 pi r derivative. So 4 pi r derivative will be 4 pi itself. And when you differentiate negative 400 over r square, 4000 over r square, take it up, negative 4000 r to the power -2. So here it is negative already, negative 4000. This is going to become -2 r to the power of -3 and plus 4 pi r. This negative and negative become positive, so 8000 over r cube plus 4 pi, and radius, I mean derivative of 4 pi r is 4 pi. Now here if I plug r as 6.83, you can see this value is coming as positive. This double derivative, if I plug r as 6.83 here, it will come as positive. Since this answer is coming as positive, so that goes under the second category, which is a minima. So what does it mean is that if I take the radius as 6.83, my volume of the solid will be surface area or the material that will be required will be minimum. Of course, accordingly the height will also change. So let's just take the evidence of this also on calculator and see how it is basically justified. So my function that I had got was 2000. I'll just erase out all these stuff. So the function that we had got was 2000 over 2000 over r plus this was the function was 2000 over r plus. So when you plot the same function here, you can see that this is the surface area function that we had got 4000 over x plus 2 pi x squared. And if you find out the, let's say, the maximum or minimum value, like let's say g solve, and let's say if I do minimum, you can see that at 6.83, the surface area is minimum. And of course, you can look at the value of the surface area as well from that part. So first, to understand the second problem, what we have here is that there is a cone from where you are cutting down a cylindrical part from the bottom, and it's what you can see is the cross-sectional view. So this is like, actually it might be like a cone like this, and from here, so let's suppose it's like a solid wood, you're cutting down like a cylindrical part here. So it's like this. I mean, not cutting down, whatever the problem context has been given. So this is how it looks like. And what you can see here is actually the cross-sectional view. So it's like you make the exact half of the section, like you cut this cone exact in half, so you'll be able to see this pattern. So let's read the problem. So the diagram shows the cross section of a hollow cone of height 30 centimeters and base radius of 12 centimeter, and a solid cylinder of radius r and height h. Both stand on the horizontal surface. It's like a hollow cone, and inside that you're fitting a cylinder. It's like this, and both stand on the horizontal surface like this. And yeah, express, so the dimension has been given that this radius is 12 for the big cone, and the radius and height of cylinders are r and h respectively, and the height of the big cone is 30 and radius is 12. So let's first try to understand the first part is that we have to express the height in terms of the radius. So how do we express the height in terms of the radius firstly? So now out here, most of the time, we need to apply similarity in such questions. So when I look at this triangle, that is this one, is actually similar to the big triangle. So the similar to this big triangle that I'm shading here. So this triangle that I've shaded is similar to the big triangle that is here. So since these dashed triangle will have this height will be basically um, this total height is 30. So this is going to be 30 minus h. Now this is the radius here. So this side is r, this side is 12, and this is nothing but going to be r as well. So this is r because you can see this opposite side of the rectangular square, you can say. And now here, let's say if I just redraw the same thing, like in this context, will be something like this. So this height that you see is total is 30 as shown here. This height is 30 minus h, and this is r, and this is 12. Since this triangle is similar to the big triangle, the respective dimensions must be in the same ratio. So now 30 minus h over 30 equals to r over 12. So the ratio of the radius and ratio of their height should be the same. So once we get this, obviously you can cross multiply and simplify. You can just bring 30 here. So 30 minus h equals to 30 over 12 times r. So what you get is, this is, if I bring it 30 here and simplify, it'll be 5 over 2 times r, and this is 30 minus h. Now if I make h the subject of the formula, h will be 30 minus 5 by 2r. So that's what we wanted to prove in the first part. So the next part is that we have to find out, express the height in terms of the radius. So height in terms of radius, and hence show that the volume V of the cylinder is given by this. Now, volume can be written as, volume is pi r square h for the cylinder, because radius is r and height is h. Now, since we got the height in terms of radius, which is 30 here, so pi times r square, 30 minus 5 over 2r. Now, if you bring in the r square inside, it'll be pi times 30r square minus 5 by 2 r cube. So that's what we wanted to prove. Now, given that r can vary, find out the volume of the largest cylinder that can stand inside the cone, and show that the cylinder occupies 4/9 the volume of the cone. So first what we'll do is, we'll first find out the derivative of this, because for maximum, now we got the volume in terms of radius. Now we'll just to find out the maximum or minimum volume, we'll do the derivative of V. So dV by dr will be, pi is a constant, so leave it as it is. Now derivative of 30r square will be 60 times r minus 5 over 2 times 3r squared. Now this equate to 0. So pi is a constant, divide other side, anyway it becomes 0. So rest what we get is 60r equals to 15 over 2 r square equals to 0. So if I take 60r equals to 15 over 2r square, r and r you can strike out, so you get r will be 120 over 15. So 120 over 15 is basically 8. So 15 8s are 120. So yeah, so 15 8s is 120. So the radius you get is 8. So this r value that you got is actually 8 now. So now what will be interesting here is that actually now find out for this radius what's the height. So when r is 8, let's find out the height. So height of the cylinder is going to be 30 minus 5 by 2 times 8. This is 4. So it'll be 30 minus 20, which is 10. So the height of the cylinder in that case is actually 10. So now let us find out if this volume of this entire cone is obviously 1/3 pi, r square will be 12 square times h is 30. So this is going to be 10. So 1440 pi is the volume of this big cone. And now volume of cylinder is basically pi r square h. So pi r square h, which is pi times radius is 12 square times radius is not 12, radius is 8 here for the cylinder. Radius is 8 square times h is 10. So it'll be 640 pi is the volume of this cylinder. Now I have to show that the volume of cylinder is 4/9 the volume of this cone. So if I divide both the volume, 640 pi over 1440 pi, this and this get cancelled. 64 over 144. If I divide it by, let's say, 16, 16 fours are and 16 nines are. So you can see that their volume ratios comes to be 4/9. And that's what we wanted to show. That's how we show these kind of problems. We solve these problems using optimization skills. So for this third example, what we basically have is that there is a rectangular sheet of the metal that is, you're cutting out these edges. From here, you're removing this piece, you're removing this piece. And then whatever is left out, you're folding. This will be folded along this. This part will be folded like here. And this part you're going to fold and make a box like this. So basically what you are getting is the wall, the base that you have is actually this. This will be the base of the box. So this part that you notice is this is the base, which is this part. So now first thing is that if we have to find out the volume of this box, what we will be doing is we'll be finding out the how much is the length of this box is, because length times the width times height, that's your volume. So length is, if you look at it, is 60 is in total. Out of that, you're cutting out, let's say the edge length is x, you're removing, this you're removing, and this is also is x. So you're removing this part basically. So this length that you notice will be 60 minus x. So this length is actually 60 minus x. Height, of course, will be, this will become the height. If I fold like this, the metal sheet, if it is being folded like here, this is the height, and that is nothing but x. So this height is x. And coming to the width, which is this length, you're cutting down from 45, cutting down 2 x's. You can see this part as well as this part. So this length will be 45 minus 2x. So length 60 minus x, width is 45 minus 2x, and height is x. So the volume of this will be length times width times height. So length is 60 minus x, width is 45 minus 2x, and height is x. So when you expand these two brackets, you will get basically x times 2700 minus 165x and plus 2x squared. This is what you're going to get. And if you open it further, multiply with x, you'll get 2700 x minus 165 x squared and plus 2x cubed, which is going to be this as the volume formula. Now our next step is to find out, given that the x can vary, find out the value of x that such that v is stationary. So obviously to do the derivative in that case, so you differentiate v with respect to x. So dv by dx will be 2700 minus 165 times 2x and plus 6x squared equals to 0. Now if you solve this equation on calculator, you get the exact values of x. So when you solve this equation, you basically get x is 45 or x is 10. But obviously you can't cut 45. This can't be 45 because this total length is 45. So you can't cut 45 from, existing plate. So this is getting ruled out. So you get 10 as the x value. So if 10 is x value, what does it mean is this 50 will be the length. 45 minus 2 times 10, which is 25, will become the width, and the height will become 10. So the volume of this shape that you've got here will be 50 times 25 times 10, which is 500 times 250, and which is 12500. So this is going to be the volume of this shape that will be stationary. So in this problem, what we have is basically the sides of this cuboid has been given x, 2x, and the height is y, and its volume has been given as 72. So you have to show that the total surface area is given by this. So basically, volume is 72. So 2x times y is 72. So y will be 72 over 2x squared, because you can see there is no y involved in the equation, which is 36 over x squared. So you got y as in terms of x. Now total surface area of any cuboid is given by 2 times length times breadth plus breadth times height plus height times length. So let's see what we get. 2 times length times breadth, so length, and let's say width is, so 2x times x plus width times height, which is x times y, and plus height times length, so y times 2x. This is x times y. Now, so what we get is 2 times 2x squared here. xy plus 2xy is plus 3xy. So you get 4x squared plus 6xy out here. And now what we do is we're going to put, in place of y, you're going to put 36 over x squared. So you put it out here. So it'll be 4x squared plus 6x plus in times 36 over x squared. And 36 times 6 is 216. So 4x squared plus 216 over x cubed. Over x, sorry. This x and x get cancelled. So you get it, exactly what we wanted. Now, given that x can vary, find out the dimension of the cuboid when a is minimum. So when you find out the derivative of a, so dA by dx, you're going to have the derivative of 4x squared will be 8x, and 216 over x, first you modify it as 216 x raised to minus 1, so it'll be minus 216 x raised to negative 2. So it'll be 8x minus 216 over x squared equals to 0. So it'll be 8x cubed over 216. If I take LCM, it'll be 8x cubed over minus 216 over x squared equals to 0. So you'll get 8x cubed equals to 216, and you get x cubed equals to 216 over 8, and then you find out cube root of 216 over 8, which is nothing but 6 over 2, which is 3. So this is going to be 27, and 27 times cube root of that is 3. So if I take x is 3, at that time, my dimension will be minimum. Obviously, you can verify using double derivative and all.